On the left is the standard form of an ellipse, aligned with the coordinate axes, making its properties immediately apparent. On the right, a general polynomial equation results in a shape translated and rotated away from the origin. Identifying the specific type and dimensions of this curve typically requires a method to simplify the equation, removing the linear and cross-product terms to find its underlying geometric parameters. Standard point plotting becomes inefficient for these general forms, as solving for y requires handling complex square roots across a nonlinear range. Instead, we can use an algebraic approach to determine the curve's properties directly. A rigorous methodology for this reduction is found in Günter and Kuzman's collection of problems in higher mathematics. Compiled in 1912 at the Institute of Engineers in St. Petersburg, this text was the primary reference for Russian mathematics departments throughout the 20th century. The text contains over 6,000 problems and was a prerequisite for the theoretical minimum examinations conducted by physicist Lev Landau. Section 1.6 of the book provides an algorithm for simplifying these equations. It treats the 2D curve as a specific case of a three-dimensional multivariable function. By applying multivariable calculus to the coefficients of the general form, we can solve these 2D geometry problems through an analytical framework. A general second-order equation in two variables consists of 6 components: the quadratic terms x squared and y squared, the xy product, linear terms for x and y, and a constant. Günter and Kuzman introduce a third variable, z. This homogenization multiplies linear terms by z and the constant by z squared, creating a ternary quadratic form. This turns the 2D equation into a 3D surface, allowing us to use partial derivatives to find its local extremum. Using Euler's identity for homogeneous functions ensures that the properties of this 3D surface accurately reflect the geometry of the original 2D curve. Moving the problem into 3D algebra allows us to apply calculus to find geometric features that are difficult to isolate in 2D. If a curve has a center of symmetry, that point corresponds to the critical point on our 3D surface. Taking partial derivatives with respect to x and y at z equals 1 gives two linear equations. Solving this locates where the 3D tangent planes are horizontal. Projecting this critical point down to the 2D plane gives the curve's geometric center. This calculus-based approach identifies the translated origin immediately without needing to complete the square or perform coordinate substitutions manually. Even with the center located, the curve remains rotated. To fix this, we look at the equation's algebraic invariance. Invariants are numerical values derived from the coefficients that do not change when the coordinate system is rotated or translated. The critical invariant is the determinant of the quadratic terms, lowercase delta, calculated as 4ac minus b squared. Its sign classifies the curve. A positive delta indicates an ellipse, a negative indicates a hyperbola, and 0 indicates a parabola. By finding the eigenvalues, represented as lambda1 and lambda2, we can determine the lengths of the curve's semiaxes and its final rotated orientation. This use of matrix invariance lets us calculate the curve's rotation using intrinsic properties of the coefficients rather than trigonometric trial and error. We can apply this method to the equation from scene 1a, which corresponds to problem 288 in the text. 16x squared plus 24xy plus 9y squared minus 170x plus 310y minus 465 equals 0. First, we calculate the determinant. 4 times 16 times 9 is 576. 24 squared is also 576. The difference is exactly 0. This 0 result confirms that the curve is a parabola. Because it is a parabola, it has no finite center of symmetry, which explains why our previous center-finding equations would not yield a unique point. Gunter and Kuzman provide a specific identity. We restructure the quadratic terms into a single squared binomial, representing the axes of the parabola. When we align our axes with this new binomial and its perpendicular, the general equation reduces to its simplest canonical form. By utilizing the algebraic invariance of the equation, we derived a new coordinate perspective that matches the physical orientation of the parabola. This process shows how a sequence of general coefficients reduces to a standard geometric shape. The Russian pedagogical tradition emphasized this integration of fields. Solving a single geometry problem required the simultaneous application of calculus and linear algebra. This was the core of the theoretical minimum, the ability to apply high-level algebraic tools to simplify complex physical and geometric systems. The result is a demonstration that second-order equations are defined by algebraic properties that remain constant, regardless of the coordinate system used to view them.